all equations dealt with thus far have involved only one variable. In other words, there has only been one unknown. As the name implies, simultaneous equations involve solving for more than one variable at the same time. We can solve a pair of linear simultaneous equations in one of three ways: by substitution, by elimination, or graphically. Substitution involves isolating one variable from one of the two equations and substituting the result into the other equation. We then solve for the one variable before substituting the value back into one of the original equations to find the second variable. Let's look at the method of substitution. Isolating one variable and substituting into the second equation. It doesn't matter which variable you wish to isolate. For simplicity's sake, we'll isolate x in the first equation. So, x equals 8 minus 2y. We'll call this equation 3. We then substitute this value for x into the second equation. So 2x plus y equals 13 becomes 2 times 8 minus 2y plus y equals 13. Solving the equation, we get y equals 1. And now that we have the value for y, we substitute it into the first equation to find the value of x.
Jane, do we have to substitute the value of y back into the first equation?
No, not at all. You can substitute y into either equation to find x. It's just easier to substitute into the simplest equation. Nice question, Samantha. The second method of elimination to solve linear simultaneous equations is by far the easiest and quickest of the three. When using this method, our aim is to match, or make similar, the coefficients of one of the variables in the two equations. In other words, we manipulate either or both of the equations until we have matching coefficients of one of the variables. Once we have done this, we then either add or subtract the newly formed equations, such that one of the variables is eliminated. The coefficient of x in the first equation is 1, and the coefficient of x in the second equation is 2. So, we will double each term of the first equation, such that the x terms match. Double x is 2x, double 2y is 4y, and double 8 is 16. Now that we have a 2x in each equation, we subtract each term of equation 2 from each term of equation 3, so that the x terms in each of these equations cancel out. In other words, the subtraction leaves us with just y as the variable to solve for. The subtraction of these equations leaves us with y equals 1. And we can now substitute this value for y into either of the original equations to find the value of x. The solution to these simultaneous equations is therefore x equals 6 and y equals 1. Benita, I'd like you to solve the pair of simultaneous equations on the board, using method 1. Tony, I'd like you to solve them using method 2.
All right. Well, first, I'd isolate x in the second equation. I then substitute 5 minus 2y in for x in the first equation. So, 2 times 5 minus 2y minus y equals 5. Multiplying and I get 10 minus 4y minus y equals 5. So, 10 minus 5 equals 4y plus y, which gives 5y equal to 5, and therefore y equals 1. I then substituted y equals 1 into the equation x equals 5 minus 2y, which gave me a value of 3 for x. So, the solution for these simultaneous equations is x equals 3 and y equals 1. How was that?
Excellent, Benita. Tony, we'll look at your solution in a bit. Tony, let's see your solution.
First, I multiplied equation 2 by 2, so that I had 2x in each equation. That gave me 2x plus 4y equals 10, which I called equation 3. I then subtracted equation 1 from equation 3, which gave me 5y equals 5. So y equals 1. To find x, I then substituted y equals 1 into equation 2. My solution to the simultaneous equations is therefore x equals 3, and y equals 1.
Nice work, Tony.
Sorry to interrupt, Jane. Tony, how did you know to double x? I mean, why didn't you double y in equation 1? Jane, how do we know which variable to manipulate?
You look very worried, Maria. It doesn't matter which variable you choose to manipulate. You will get the same solution. There's no right or wrong way. But as a general tip, select the positive variable as the variable you wish to manipulate. To prove that it doesn't make a difference, why don't you solve the simultaneous equations by manipulating equation 1, as opposed to equation 2?
Okay. Well, if I double equation 1, I get 4x minus 2y equals 10. I then subtract equation 2 from equation 3, which gives me 3x minus 4y equals 5. Okay. What have I done wrong? The y's didn't cancel out.
Okay, let's look at that a little closer. You doubled each term in equation 1 just fine. But when it came to eliminating y from each equation, you subtracted equation 2 from equation 3, instead of adding equation 2 to equation 3. The whole purpose of subtracting the two equations is to eliminate one of the variables, such that we can solve for the other variable. I know I said we subtract the two equations earlier, but in essence what we are doing is to match a variable in the two equations, such that the coefficient of the variable in each equation is similar, or identical. To clarify what I'm talking about, let's go back to Tony's solution. When Tony doubled each term in equation 2, the x terms in equation 1 and equation 3 were identical. In other words, their signs and coefficients were the same, plus 2x. So he subtracted the terms in equation 1 from the terms in equation 3, because this would eliminate the x terms. 2x minus 2x equals 0. We then do likewise for the rest of the terms in each equation. 4y minus y, which equals 4y plus y, which is 5y. And 10 minus 5 is 5. What we are effectively doing is changing the sign of each term of the bottom equation, and adding the two equations together. So, 2x plus minus 2x is 0. 4y plus y is 5y. And 10 plus minus 5 is 5. Does all that make sense?
Yes, I'm with you so far.
Great. Let's get back to your problem. The y term in equation 3 is minus 2y, and the y term in equation 2 is plus 2y. Thus, in order to eliminate y, we simply add the two equations, because we have conflicting signs for 2y. Thus, 4x plus x is 5x, minus 2y plus 2y is 0, and 10 plus 5 is 15. So, 5x equals 15, which means x equals 3. Take it from there, Maria.
Okay. Substituting x equals 3 into equation 2, I get 3 plus 2y equals 5, which means 2y equals 5 minus 3, and that gives me y equal to 1. I get it now. Thanks for that explanation, Jane.
Sure, Maria. What we just did with substitution and elimination was to solve a pair of simultaneous equations, algebraically. Simultaneous equations can also be solved graphically, which is what we'll be doing next. The third and final way of solving linear simultaneous equations is by sketching straight-line graphs. When sketching a straight-line graph, we need to know the x and y intercepts. Recall that to find the x-intercept we put y equal to 0, and to find the y-intercept we put x equal to 0. Thus, To find the x-intercept of x plus y equals 12, we put y equal to 0, which means x equals 12. Thus, the x-intercept of this line is the point 12, 0. To find the y-intercept, we put x equal to 0. So, 0 plus y equals 12, which means y equals 12. And therefore the y-intercept is the point 0, 12. We can now sketch the graph by plotting these 2 points and drawing a straight line through them. We proceed similarly to find the x and y intercepts of the line x minus y equals 4, and sketching the graph. The solution to these simultaneous equations will be the point of intersection, 8, 4. Solving linear simultaneous equations graphically is rarely used though, particularly when the equations themselves are not as straightforward as these two. Solving linear simultaneous equations by elimination is the quickest and easiest method to use, even though you may use any method you wish. That concludes linear simultaneous equations. We'll be moving on to word problems that involve linear equations next.